Hi everyone, we're going to be looking at the action of heat on metal compounds. So you will have to know the action of heat on metal hydroxide, metal carbonates and metal nitrates. So when heated, some compounds will break down into new products, and this is called thermal decomposition. Now, metal hydroxides of very reactive metals like potassium hydroxide and sodium hydroxide, they are unaffected by heat, but other metal hydroxides that are down the reactivity series, those listed in here, they will decompose to give metal oxide and water. In this reaction, the only thing that we can test here is the presence of water. So you will see droplets of water on the rim of the test tube, and you can test for the presence of water using either cobalt chloride paper, which turns from blue to pink in the presence of water, or anhydrous copper 2 sulfate, which turns from white to blue in the presence of water. For example, you can have the decomposition of calcium hydroxide to give you calcium oxide and water. And as you can see, the equation is already balanced. Here we can see calcium hydroxide, which is being strongly heated by a Bunsen burner, and on heating it's going to undergo thermal decomposition to give calcium oxide and water. We'll see the water at the mouth of the test tube as droplets, and the water can be tested using cobalt chloride paper, which is going to change from blue to pink. Now let's see the action of heat on metal carbonates. Now metal carbonates, again, the metal carbonates that are formed by metals high in the reactivity series like potassium carbonate and sodium carbonate, they are unaffected by heat, they will not decompose, but other carbonates from metals down the reactivity series will decompose to give metal oxide and carbon dioxide. Now this carbon dioxide can be tested using lime water, so the gas that is produced is bubbled through lime water. For example, you can have the decomposition of zinc carbonate to give zinc oxide plus carbon dioxide, and this equation is already balanced. Here you can see the thermal decomposition of copper carbonate. Copper carbonate is normally green in color, and on strong heating, it's going to decompose to give you copper oxide, the black solid which is being formed from the bottom top. This reaction gives carbon dioxide. The carbon dioxide can be bubbled in lime water. It's going to turn milky, indicating the positive result for carbon dioxide gas. Now let's see the action of heat on metal nitrates. Now for metal nitrates of metals that are high in the reactivity series like potassium nitrate and sodium nitrate, we're going to have the decomposition to produce metal nitride and oxygen. So for example, here you have potassium nitrate decomposing, so on the arrow there's nothing, decomposing to give potassium nitride, this is nitride, plus oxygen, so oxygen gas. We can try to write the equation for sodium as well. So sodium nitrate will give sodium nitride and oxygen gas, and we balance by putting half. Now for other metals that are down in the reactivity series, they will decompose to give the metal oxide, nitrogen dioxide and oxygen. Now oxygen can be tested using a glowing splint, so it's going to relight in the presence of oxygen, and nitrogen dioxide, this is a brown gas, and this is a toxic gas as it is highly acidic. So we can write an equation for calcium nitrate. So this is going to decompose to give you the calcium oxide, nitrogen dioxide, and oxygen gas. And we can balance the equation by putting a 2 here. So to summarize the decomposition of metal compounds, so for hydroxides, potassium and sodium will not decompose. For calcium, magnesium, zinc, iron, lead, and copper, these are metals that are lower down in the reactivity series. Their hydroxide will decompose to give metal oxide and water. For the carbonates, they will decompose to give metal oxide plus carbon dioxide. And for potassium and sodium nitrates, these will give metal nitride plus oxygen gas. And for calcium, magnesium, zinc, iron, lead, and copper nitrates, they will give metal oxide plus nitrogen dioxide plus oxygen.